Hi, my name is Bryce Parkasevich, and today I will be doing a presentation on my project, which was search-based algorithms and Q-learning algorithms in the game Snake. So I'll just start my slideshow here. And so the algorithms that I used for trying to solve the game Snake were a breadth first search, an A-star search, and some variations of Q-learning algorithms. So first, the search-based algorithms. For the breadth first search, I used a standard breadth first search algorithm using a queue for the fringe elements. And what it ended up showing was that it was fairly slow, and it moved on the x-axis and then on the y-axis to get to the apple, as opposed to the A-star search, which I'll explain in a second. And it was also very predictable in its ability to search and find the apple. The A-star search was slightly altered. It uses a priority queue instead of a regular queue to get the fringe elements. The priority was made up of the Euclidean distance plus the cost of the movements to get to the goal, which was 1 unit per movement. That's the G and the H. It was also fairly slow in moving and tended to have more of a zigzag pattern when it came to the actual motion that it presented for moving towards the apple. The apple in Snake is the goal. The Q-learning aspect of my presentation of my project was utilizing the Q update equation for Q-learning, which I have written here. And I used epsilon to decide whether to make a random move or a Q-based move in the training. So the Q-learning was made of two different parts. It was made of training the algorithm, which is essentially just creating the Q values for each state action pair on the board, and then sending it the policy to a final computer to run the entire policy to see if it ends up being a good policy or a bad policy, to see whether it gets a lot of apples or it gets no apples, or if it wins the game, which really didn't happen for either the search algorithms or the Q-learning. The state that I used in finding the Q value included the head position, X and Y values for the snake's head, and its relative position compared to the apple, whether it's to the left, to the right, up or down relative to the apple. Without having the apple involved, the algorithm only learns based off of where the snake's head is, and so the Q values are based purely on where the snake is located, and that is not always going to mean that the apple is anywhere near that space, since the apple moves randomly from space to space every iteration. Every time the snake gets the apple, it moves to a random location. So it is necessary to put, at least, at the very least, the relative position of the apple in as part of the state. I trained it for a certain number of episodes before switching to giving the trained values to the computer to use as a policy. And throughout, to find different variations of how Q-learning and different parameter changes affect the learning process, I altered epsilon, alpha, the discount, the sample complexity, and the regret to see effects on the output policy. What I found after running it many times is the actual playthrough of the snake getting the apples is very fast compared to the search-based algorithms. This is because it's just following very discrete, like it's either it already knows which way it's going to go, as opposed to the search-based algorithm, which needs to find which way it's going to go every step of the way. One downside of the Q learning, though, is that sometimes they would get, well, oftentimes they would get caught in local maximas and cause the snake to just go in circles forever, because the Q values ended up evening out in a space to be uh, as a good spot, but not the best spot. And it would just stay in that spot because any state off of that spot is less than states in that spot. So essentially, it would just go in circles. And so I had to find a way around that, which involved using the escape key so that I can still run tests, and just stop the program if it starts going in circles. The results for the breadth first search had roughly a mean score of about 484 with a mean time of about 112.59 seconds. And its mean score per second was about 4.3 points a second, which ended up being a pretty good score. A star, the mean score was 575, a little bit better. The mean time was 124 seconds, which was a little bit longer. And the mean score per second was definitely better than the breadth first search. A star showed a slight improvement over breadth first search, but in terms of the ratio of score to time, they are very similar when trying to find results in the game of Snake. As for results of Q learning, I have a variety of different results. So that'll be the next few slides are just some results from the Q learning algorithms. The best results I found and what I used as kind of my baseline for trying out different values for alpha, epsilon, the complexity, and the discount and the rewards ended up being 1,000 trials with an alpha of 0.2, an epsilon of 0.5, and a discount of 1. It had a living reward of -1, an apple reward of +9, and a death reward of -11. For this Q learning algorithm, the mean score was around 117, which is close to between 11 and 12 apples. The mean time was around 13.96 seconds, much faster than either of the search algorithms, but it also didn't get as many apples. So to try and adjust for that, I put the mean points per second, which was 8.38, much better ratio than it's almost double the ratio of the search-based algorithms. Unfortunately, using these parameters, it would still get stuck in loops around 40% of the time. But I would just count that as it ending, so the game finishing. So I would still count the apples that I got before it went into the loop still counted towards its mean score. As what is probably obvious, but I tried it anyways, is the complexity. I halved it, so only about 500 trials, and it kept everything else the same. The mean score dropped significantly. So did the mean time, but even the ratio is significantly less than the original 1,000 trials. With a mean score of only 42, which is only about 4 apples, mean time around 7.5 seconds. And the mean score per second was still better than the search-based algorithms, with 5.53, but it got stuck in the loop 80% of the time. The rest of these I changed alpha, and it's changing alpha from 0.2 to 0.8 was relatively close to doing about 500 trials. Then I changed the discount to 0.1, and it drastically dropped the ability to play the game. Mean score of only 1, and mean score per second of only about 1, and it got stuck in a loop 95% of the time. And then changing the living reward to 0 and the apple reward to +10, the death reward to -10. Again, it was even worse. The living reward seemed to play a big impact on whether or not the snake would be able to find the apple and find the goal consistently, and it got stuck in the loop 90% of the time. So, in conclusion, the search algorithms were slow to move but had consistently high scores. Movement was predictable and it had a low score to second ratio, score to time ratio. And on top of that, there was no looping. The Q learning algorithms were very quick to move, but they had some random movement even at high complexity. Scores were lower than the search algorithms overall for all of them, but it was capable of a very high score to time ratio. The biggest flaw is that it would get stuck in relative maxima and loop around. So overall, I would say that the search-based algorithm was a better choice for finding the apples. Q-learning it's nice because it doesn't require you to have the apple to know exactly where the apple is. But in the game of Snake, the player's always going to actually know where the apple is. So the search-based algorithm, it just is a lot more relatable to what a player is actually going to be going through while playing the game, and ultimately seem to be the better algorithm. Here, I'm going to show you just a snippet of what A-star search looked like. And it'll run, and this is my snake game. So as you can see, it goes towards the apple, finds the apple, and then continues to find the next location as the apple. This is the A-star search. So as you can see, it is going in a zigzag pattern towards the apple. That's because the priority is based on the Euclidean distance, which is a direct line towards the apple. So it's constantly trying to get as close to the apple as possible while moving forward. I would show my reinforcement learning, but it takes a long time for it to train, and I wouldn't be able to fit that into this 15-minute video. But the A-star gets a very high score. As you can see, it's still going, and it very much understands where the apple is, what it has to do to make the movements to get the apple. So this will run for a while. It usually takes about 2, maybe 3 minutes to get into a state where it can't move anymore. The states where it can't move anymore tend to be when the apple goes inside of a loop that the snake created, and then the snake gets the apple and can't get out of the loop in time before its tail comes into a place where it can actually escape. But as you can see, it's very smart. Even if it's close to being closed in, if it knows it can get out in a certain amount of time, it will still get out. So I'll stop this here. Oh, and it just collided. So I'll stop this here. And thank you for watching my presentation. I hope you found it informative. And if there's any questions, you can shoot me an email at bpark4@unh.newhaven.edu. Thank you.